Our fifth and final lesson in Unit 3, Focus on Transformation, deals with symmetry. And we're quite familiar with the concept of symmetry. Even from a young age, we understand reflectional symmetry. And part of that is just kind of looking in the mirror and knowing that there is a degree of reflectional symmetry in the way that our bodies are designed. And we're going to take that kind of a step further here in high school geometry and think about symmetry in more ways than just reflectional or line symmetry. So we're going to explore these two different types of symmetry in two-dimensional figures. That's our goal for the day. And so let's talk about these two different types of symmetry. First, reflectional symmetry. This is what we're already familiar with. Symmetry for which a reflection will map a figure back onto itself. And that's different from rotational symmetry, where we turn the figure and then it maps back onto itself. So for example, even if we're looking at this really long rectangle that I'm going to call this meter stick right here, there's a line of symmetry right down the middle so that this would reflect onto itself, right? And it'd be the same figure. There is reflectional symmetry on the line that divides this in half so that we could flip it over onto itself and it would be the same size and same shape. But then there's also rotational symmetry, where we could rotate this a full 180 degrees and it would map back onto itself with congruent sides and congruent angles. And so there is a little bit of exploration around rotational symmetry that might be tough for you today. Engaging with this, thinking through this, but mostly it's visualizing it. It's really difficult to explain why there is or when there is reflectional symmetry, right? But it's something that you see and it's something that you acknowledge, and it's something that if you understand what reflectional symmetry is, you get it when you see it. And the same is probably true and most likely true for rotational symmetry. So this kind of depends on your ability to think about what you're seeing. Now there's some spots in here that I can be of particular helpfulness, like why with a rectangle does it have to rotate a full 180 degrees to get mapped back onto itself, and then the full 360 to get back to where it started. We'll chat through that as we explore these different types of symmetries. So here again are just a couple examples for reflectional and rotational symmetry. And so in this case, this figure right here, we can see that there's a line of reflection there, that this vertical line M, if I were to reflect this figure over line M, which passes right through the middle of this figure, then it would map back onto itself. Horizontal line N, if I rotate it this direction, or reflect it that direction, it will map back onto itself. With rotational symmetry, it maybe is a little bit harder for us to see that, but we would rotate this usually through the center is how that rotational symmetry is going to work. And if we spin this around, it could go 180 degrees and it would map back onto itself, and then another 180 degrees and it would be back to where it started. And so we name the rotational symmetry using the rotation notation that we had in our lesson 3. And we're going to have reflectional symmetry notated like we did reflectional symmetry back in lesson 2. So we're going to sort of just support that as we review that, and we're going to revisit that stuff to make us hopefully better understand lesson 2 and lesson 3 as we think through and explain lesson 5. So here are a couple examples. Copy these figures on your paper. And I want you to think like what transformations would map this image back onto itself. And so if we're thinking in terms of these rigid motions, these transformations, the main thing that I want for us to engage with and think through is, first of all and foremost, this reflectional symmetry. I could reflect this over this line here. I could reflect it over that line, and it would map it back onto itself. All right, what if I drew a line this direction? Would that reflect it back onto itself? Hopefully you can tell that the answer there would be no, because this is thicker than that. So this picture would come out like so if I were to reflect it, right? Whereas this then would be, whoops, actually it'd probably be a little bit taller, right? A little bit taller there. And then the skinny piece would be like there. And then again, thick piece right there. So if I reflect it over that line, it's not going to match up quite so perfectly. So we want to be very aware of where do we draw our lines of reflection. Generally speaking, we're going to be cutting the picture in half. But sometimes that picture can be cut in half along a diagonal as well. So don't just think of vertical and horizontal lines of reflection. So these would be two lines of reflection that we could use. Over here, the line of reflection would have to be just this one. There's not another line of reflection that I could use to make that work. Now there is rotational symmetry, 180 degrees, about that center. I'm just going to use C as our center. That's usually where we're going to be rotating about, is the center, so that things match up perfectly on the other side. But we should note that that's going to have to be 180 degrees to map this figure back onto itself. And we're going to explore a little bit about why it's not 90, all right, as we continue to think through this work. Dealing with regular polygons. All right, now regular polygons are a little bit interesting. So let's talk about just lines of symmetry. We're not going to talk about rotations quite yet. But in these figures, a regular hexagon, again, let's explain what a regular hexagon is. So hexagon is where the number of sides, which we usually say n, is 6. There are 6 sides. There's 6 angles. And regular means that all 6 sides are congruent, and then all 6 angles are congruent. 6 congruent sides and 6 congruent angles. All right, there's 6 sides, there's 6 angles. That's how we know that it's a hexagon. Regular means that all the sides are congruent, all of the angles are congruent. So we can imagine, and we can visualize, we can understand that in this hexagon, there's going to be a line of symmetry through the vertical, right, from top to bottom, all right, through the side. And then we can also tell that there's going to be a line of symmetry horizontally, all right? So we get the horizontal and the vertical. I'm not usually worried about horizontal and vertical. But what I want to make sure that you understand is no matter which way I am looking at this, this picture, if you were to draw it on your paper and then turn your paper several different ways, you'd notice that there's a line of symmetry that passes through the midpoint of each of our sides, all right? A line of reflectional symmetry through the midpoint of each of our sides. And just like there's this one horizontal that passes through these opposite vertices, we could also draw a line of reflectional symmetry that passes through the other pairs of vertexes, all right, of vertices. And so we have 1, 2, 3 lines of reflectional symmetry that go through the opposite vertices. And then we also have 1, 2, 3 lines of reflectional symmetry that pass through the sides. So we have a total of 6 lines of reflectional symmetry. How many sides does a hexagon have? Oh, it has 6. How many angles does it have? It has 6. How many lines of reflectional symmetry does it have? 6. All right, so that's really important that you're able to kind of connect those dots when it comes to these regular polygons. If we had a regular quadrilateral, that's a fancy name for a square, how many lines of reflection does a square have? All right, think about the number of sides, think about the number of angles, and then think about the number of lines of reflectional symmetry. Identify all the lines of symmetry, and how do you know when you have found them all? So we're just going to talk about lines of reflectional symmetry. When it says lines of symmetry, it's talking about reflectional symmetry. All right, so you try to do this one, example 2b. Now describing and discussing rotational symmetry. So pause the video if you need to finish that last one. So example 3 here, we're going to focus on rotational symmetry. So we want to understand what it means to rotate this figure through space. The easiest thing that you can do that I'm not able to do on this because these are in the diagram and these are on the, I don't have control over these, but is if you draw this on your paper, you should be able to rotate your paper so that this figure lines up the way that it was before you started rotating it. And what you'll notice is that this has rotational symmetry every 120 degrees. But where does this come from? Why is it 120 degrees? Now, when we think about equilateral triangles, we know that the measure of the angles are each 60 degrees. All right, we know that from middle grades or whatever else. But an equilateral triangle, is also equiangular, and so there's 180 degrees divided by 3 means that each one is 60 degrees. So we know that, but why is this rotational symmetry happening at 120 degrees? Why do we know that this angle is going to be 120? I'll draw this 120 and 120. So what I want for you to understand with respect to the fact that this rotation happens every 120 degrees is because at the center, drawing a segment to each vertex, it cuts that whole center into 1, 2, 3 pieces, all right? And each of those pieces is going to be 120 degrees. Now, why do we know that that's 120 degrees? Well, the reason is because if we have 360 degrees total and we're dividing it 3 ways, then that means that there is 120 degrees at that central angle, all right? So this central angle is 120, this central angle is 120, that central angle is 120 degrees. Which means that if I turn this triangle 120 degrees, then point B is going to go to A is going to go to C, and C is going to go to B if I do that 120 degrees. But then here's what's awesome about this. I could do it another 120 degrees, which would get us up to 240, 120 plus 120. And then I could do it a third time, but that would get me to 360. And I don't count the 360 as a rotational symmetry because that's just back to where it started. Just like I don't count 0 degrees as rotational symmetry. If we're not moving it or moving it all the way around, that doesn't count as symmetrical. All right, but you'll see this every 120 degrees. So you're going to do 120, and then 120 plus 120 makes 240, and then the next one is 360. So the way that we would talk about this is we would say that there's rotational symmetry for 120 degrees about the center, and there's rotational symmetry, lowercase r, 240 degrees about the center. If you do not have the little degrees symbol, that is completely okay with me. I know that maybe future teachers might be upset about not using the units on there, but we know that it's degrees in this class. Rotational symmetry around the center. Now this is not a regular polygon, and so how do I know that this is not going to be is it going to be 60 degrees? Is it going to be 90 degrees? Is it going to be some other weird number? How do we figure that out? Well, folks, hopefully you can tell that this, if I were to rotate it just 90 degrees, then that picture, it's going to be hard for me to draw, that picture is going to look like this if I rotate it just 90 degrees, right? So we know that it's not going to be 90. If we go another 90 degrees, then we should see that this lines up more nicely. I did not draw that correctly. It's close, but you guys get the idea. You get the gist of this. It's supposed to be like this. I gotta have it go the other direction, and it's really bugging me because I want to do a good job. All right, so I did an even worse job. But you get the idea. If I rotate this 90 degrees, it's not going to overlap. But if I go another 90, you can picture that it will. Again, if you're turning your paper 90 degrees, you're like, that doesn't match. Do it another 90 degrees. Okay, it does. Or if you have cutouts that are congruent to these, then you can flip the cutout and see how that lines up. But we want to rotate that about that center, that point of symmetry. So you can either use P or you can use C for that notation. I don't have a preference. I don't care how you do. All right. So I want for you to try this. This is again is rotational symmetry, and I want you to think about how we can find the degrees of rotational symmetry about the center of rotation. Now you can call that point C or you can call it point P, whatever you want to do. We're not drawing lines of reflection, although lines of reflection aren't unhelpful here. It is stuff that you can consider doing, but I really care about what are going to be the rotational symmetry for the figures, and does it have symmetry about that one point, that 180 degree rotation just one time. That's called, again, point symmetry from the last slide. All right, what type of symmetry does this figure have? Or how about this? What are the types of symmetry that you can find in this diagram? So here we have a picture of a flower, and it looks to me that we've got, again, reflectional symmetry. 1, 2, 3, 4, 5 times. You can kind of see a pentagon here, a regular pentagon. So we know there's 5 lines of reflectional symmetry. Are there also iterations of rotational symmetry? And so let's consider that. If I were to move this that far, all right, this whole picture would line back up again. So the question is, what is the measure of that angle? All right, well, that angle is going to be the same as the measure of this angle, which is going to be the same as the measure for that angle, which is going to be the same as that, which is going to be the same as that. So how many of these little arcs do I have? 1 slice of pizza, 2, 3, 4, whoops. There's 5 slices of pizza there. All right, so we're going to take our 360 degrees and divide that by 5 to find out that we have rotations every 72 degrees until we get back to 360. So the way that we will think through that is, again, a little bit tough. Why did I divide by 5? Well, there were 5 slices of pie there. There's 5 petals. This is basically a pentagonal shape, whether we can recognize that well. It's not, it's not a pentagon, but it follows that same pattern that we're going to see with a regular pentagon. And so that means that we're going to have rotational symmetry. Besides this line symmetry about line 1, 2, 3, 4, 5, we're also going to have rotational symmetry every 72 degrees about that center point. Now you can call it P or you can call it C, whatever you want to call it. But if we're doing rotational symmetry every 72 degrees, then we're going to have to do some calculator work to add 72 and 72, and then 72 and 72, and then 72, all the way to where we get to 360, all right? But I don't count the 360. So that means that we're going to have 4 of these. We're going to have 1, 2, 3, 4 of those rotations because the 5th one takes us back to 0. So go ahead and fill out the other the other rotations for how many degrees we are going to rotate. All right? So basically you're just adding another 72 and another 72. That's how that's going to go. So we're going to talk about how this has rotational symmetry and it has reflectional symmetry. We're going to draw all those lines of symmetry for reflectional symmetry, and we're going to count all of the degrees for which they are rotated for the rotational symmetry. I didn't realize that was all printed in there. All right. So now I want for you to try to do this. You have to imagine where is the center of rotational symmetry, and are there any lines of reflectional symmetry? So think on that. This was, I thought that this was a you do. It's not a you do, this is a me do. So this has no reflectional symmetry, right? If I draw this line of reflection, this dot will come up here and that dot will come up there, and it doesn't match the original. If I go like this is gonna come over here, I don't have a dot there. This is gonna go over there, I don't have a dot there. If we go corner to corner, this isn't gonna map correctly, right? It's not gonna line up with the way that it ought to. If I go like so, that's going to put this corner out there. This corner is going to be up here, so it's not mapping back to where it goes. This has no reflectional symmetry, but it does have point symmetry. It has 180 degrees rotational symmetry about the center. So if this is the center, this can move 180 degrees there, this can move 180 degrees there, this corner goes over to that corner, this corner goes there, this corner goes to that corner, this corner goes to that corner. So this does have rotational symmetry about the center, 180 degrees, so point symmetry, but it does not have any other symmetries. All right, hopefully now you can kind of think about these figures and what sort of symmetries they have. One strategy, again, that I want to encourage you to think about is having a cutout that you could then rotate, or since you're not going to be cutting up your papers, you're probably just going to rotate your actual document so that you can see how your figure does rotate to match back up with where your neighbor's is, all right? Can you make that picture look the same as theirs that is unrotated, all right? And so this again is just identifying those symmetries and exploring not just reflectional line symmetry like you did in your elementary art classes, but then thinking also about rotational symmetry.